All right. We're going to do our 10.5 ISN as usual first before we do the 10.5 lesson. And if I get my little thing to work here, get it up here. Tangents to circles is the topic for today. A tangent to a circle. Oh, pen, please. A tangent to a circle intersects the circle in exactly one point, called the point of tangency. So right here, where it touches the circle, that is your point of tangency. Okay, a tangent line doesn't have to have arrows on it. Okay, it's just a line that touches the circle in exactly one point. It may look like it touches it in more, but that is intended to be just one little dot. Skims the circle. There are important relationships involving tangents that we're going to learn. Now, there's also something called a common tangent. A common tangent is a line, ray, or segment that is tangent to two circles in the same plane. So these two circles are in the same plane, and there's a tangent line that runs between them in this particular case on this one. And this tangent line runs on the same side of the circles. The points of tangency would be approximately here and here on those two circles, and about here and here on these. The next real important thing about a tangent is a line is tangent to a circle if and only if it's perpendicular. So to prove that a line is tangent to a circle, you could use the Pythagorean theorem. To prove that that line is tangent to that circle, you would need to know for sure that RP is perpendicular, which would mean what right here? Yes, Nathan, a right angle. So we would definitely have a right angle there if that was a line of tangency, because RP is clearly a radius. So if RS is perpendicular to RP, I should have put that in blue as opposed to this one. RP is my pink one. So if I want to color code it, that's what it looks like. Then SR is tangent to the circle with center P. All right, if S, then the converse of that is true. If SR is tangent to the circle with center P, then RS and RP must be perpendicular. If the other thing about tangents that we're going to use today is if two segments from the same exterior point, these are both tangents, and this is a common exterior point out here. If they both come from the same point, then these tangents are congruent in length. So SR and ST, well, S must be out here then. Let's label it. And R here at the point of tangency, and T down here at that point of tangency. So if RS and ST come from S, same point, then they have to be the same length. Okay, so now let's do some examples utilizing those two properties. Example, it says segment AB is tangent to the circle with center C. So segment AB is the tangent. Segment BC is a radius. Okay. And do you see another radius in here? That's something I've noticed that we're not identifying very well sometimes, is that all radii are congruent. And there are other radii drawn in this picture, except there's no point where there is a point where it ends. Where's another radius? Yeah, DC. So this would be equal to that radius, which means that we can put a number value on it because we know BC is 8. We know DC is also 8. Okay, so CD is a radius, so CD is 8. And then AC would be 9 plus 8, which is 17. Now we can find, since we know that, bless you, we know that AB is a tangent and BC is a radius. If that's the case, then what kind of angle's up here by B? That was the first property we just, okay, 90 degrees. It has to be perpendicular. So that means we have a right triangle. Bless you, in that right triangle, this X value is a leg of the triangle. The radius is a leg of that triangle. And the 17 is the what? Hypotenuse, yes. All right, so we know the formula is leg squared plus, you got to get this down. We've gone, that's right. Leg squared plus leg squared equals hypotenuse squared. So we take the leg x and 8. X squared plus 8 squared equals 17 squared. Okay, is that a cold or allergies, Cade? Yeah. That time of year. Okay. All right, so I'm sorry, but we'll deal with it, right? X squared equals 289 minus 64b 225. Take the square root, and what do you got? So it would be 15. Wrote a little bit big there. I kind of squished that in. All right, we're good? So you got to remember when we're finding a leg, you're not adding and you're not squaring and adding and then square root. You have to do a subtraction. All right, what property we will use on this is that if you have a common exterior point and two tangents are drawn from that point, then those two tangents must be congruent. So these are equal in length. So real simple for this one, x plus 3 equals 7. Subtract 3 from both sides and we get x is equal to 4. All right, and number 2, because we have a tangent line ZB and a radius YZ, there has to be a right angle then where Z is. Angle YZB is a right angle. We have a right triangle. This little piece from A to B is given to be 8. What would Y to A be? Y to A? Y to Z is 21. What's Y to A then? It's also a radius, guys, so it's 21. All right, so now we have, and we could draw it out here if you like, for extra visual. This is Z down here. We have 21 for the radius. What would the total from Y to B then be? Yeah, 29. 21 plus 8. And then down here, we're trying to find X, the length from from Z to B. Again, that is a leg that you're trying to find because it makes the right angle. The longest side in a right triangle, of course, is the hypotenuse. So we got to do leg squared plus leg squared equals hypotenuse squared. X squared plus 21 squared equals 29 squared. 21 squared is 441. And if I remember correctly, 29 squared is 841. Did I do that right? Thank you. If I subtract 441 from both sides, I end up with x squared is 400. And then I take the square root of 400. That's 20. All right, so we just did again, found something with our Pythagorean theorem. I mean, in case you haven't realized, we've used Pythagorean theorem in very many chapters since the beginning of school. All right, now we're going to talk about tangents continued with, and talk about them in relationship to circumscribed polygons. because we're not doing 10.6 and 10.7 this year. Okay, that I do that in honors geometry, but we are going to not do 10.6 and 10.7 because we have other stuff we need to get to. So I have the option of doing them or not doing them, and they're not on the chapter test. So I think we're going to just skip them so we make sure we have plenty of time. Okay. Anyway, circumscribed polygons, that just means when you have a polygon drawn around a circle. Okay. So when a polygon is circumscribed about a circle, all of the sides of the polygon are tangent to the circle. What does this mean about congruent segments? Well, if you have a square, GHJK, and it's circumscribed about a circle with center Q, then GH, HJ, JK, and KG are all tangent lines to the circle. All right, so they have midpoints. So what I could be able to say is that if that is circumscribed about the circle, what do you think happens if that's the center point? Then this would be equal, and this would be equal, right? Squares have the same length of sides. All sides are congruent in a square, so these would be equal to those too, wouldn't they? And then it would be true going the other way as well. So all of these little segments are congruent. Here's an example of how to use that. Remember that tangent points from the exterior of a circle, points that are outside of a circle, and you draw the tangent lines to the circle have to be equal, which would mean that I'm going to do some highlighting here. If you like to do highlighting, I'm going to use 4 colors. PB would be congruent to BE. EC would be congruent to FC. AF would be congruent to AD. And with that in mind, we can find the perimeter of this triangle. And we can fill in all these numbers. So since these pink ones are congruent, if that's 6, I can put a 6 here. Oh, I meant to change color there. If this is 8, where FC is, then EC is 8. And if AF is 12, AD is 12. All right, we have a bunch of pairs of numbers to find the perimeter of the figure now. So to find the perimeter of the figure, we're just going to add up all the sides. So the perimeter, P, would be found by doing 6 plus 6 plus 8 plus 8. Does anybody see a shortcut to typing that? Plus 12 plus 12. Couldn't you just do 2 times 6 plus 2 times 8 plus 2 times 12? You add just 1 each, you mean, and then multiply by 2? Yeah, you could do that. All right, so we got, let's see, that's 20, 40, 52, isn't it? 52 units around. For each figure, find X, then find the perimeter is the next section's direction. Did anybody still need that page that I was on? We're good. Okay. So I like, just make sure you don't repeat any adding. I just make you add them in pairs. It's the easiest way to go about it. But if I wanted to find X, well, that's 13, so this is 13. I don't really need all these, but we have to do the perimeters, so might as well find them all. I don't need it to find X necessarily. But that's 17, so this is 17. And then going this way, if this is 10, then the one over here is 10. All right, so how we're going to find, should have made these connect, but X will be, yep, 13 plus 10, so X will be 23. How'd you get that? So you just added 17 and 13 and 10 and doubled it. That will work. That is a strategy. Adding these, you get 30, another, well, sorry, 30 here, 23 here, and 27 there. I don't know, whatever way you want to do it to get the perimeter, or you can just add them in pairs. 34, 44, 54 plus 6 would be, oh, I didn't add that right. 26, 34, 7, is it, how much, what did it come out to? Did you say 80? And you want to just label it units since we don't have a measurement. Does everybody agree with 80? Okay, next one, what are we going to do to find x? Find x first. Ignore the rest for just a moment. Michael? Yes. Okay, that's our first equation. So to find x, let's do x plus 2 equals 8. Subtract 2, of course, and get x's 6. All right, now we got to find the perimeter. So it'd probably be good to just go ahead and label them all. It's up to you how you choose to do it. These two are equal, so that's 5, and this is 5. So we got pairs of numbers. Make sure you just have sets of 2, and we should be good. That's 4. This is 4. And this one's 9. This one's 9. All right, so to get the perimeter, we're going to 8 plus 8 plus 5 plus 5 plus 9 plus 9 plus 4 plus 4, or whatever order you like. Is that 52 units? Okay. And this is just a little vocab review, and then we're going to do some more in our packet. Remember, a chord is just a segment that has its endpoints on the circle. A diameter is a special chord. Make sure you realize they're writing diameter for that entire thing across. A radius is what this says, and I had some students couldn't read this first hour, so this is a radius. Okay. This one is a secant, but we actually are skipping the section. We talked about what a secant was. How does a secant differ from a chord? All the way through, and it keeps going. Okay, so the chord stops, has endpoints. It's definitely only a segment, whereas a secant is a line that passes through the circle. Now, a diameter, again, goes all the way across. A radius is just from the center to the side. And today, the tangent line is simply a line that touches the circle in a point of tangency. All right, so now we'll go and look at our packet that you picked up off the podium. Review the terminology that we just went over briefly. This is a point of tangency. You have that picture, I believe, on your packet. Yes. Not much else you need to write there. These are the points of tangency for the little circles there. This is a common tangent between two circles. So sometimes people call it an interior common tangent. Yeah, this is a package. Yes. This is a common tangent as well. The points of tangency would be here and here. It can be a line, a ray, or a segment that is tangent to two circles in the same plane. These are just some other pictures I added in about that they might look like. Okay, a tangent is a line is tangent to a circle if and only if it's perpendicular to the perpendicular to the radius at the point of tangency. This would have to be a right angle for this diagram, for that to be a tangent line. You could also draw one from here to here, and then that would give you angle PTS. If TS is a point of tangency, this would have to be a right angle as well. And the converse is also true. All right. You have a picture like this. If two segments from the same exterior point are tangent to a circle, then they are congruent. So these two tangents are congruent to one another. Okay, and that picture we already dealt with. Assume that segments appear to be tangent are tangent. So if these are 12, look how easy number 1 is. What's x? Yeah, quickly, right, 12 units. We will have to do a little more work on number 2 in that JK is a tangent line. JH is a radius, and if JK is a tangent, then it has to be perpendicular to the radius at the point of tangency. So we got a leg, and we're going to find the hypotenuse. So 15 squared plus 20 squared equals x squared. We got 225 plus 400 equals x squared, and I realize you guys probably just typed that on your calculator and got 625 right away. Take the square root, and what do we got for x? Okay. 25 units, I guess. Cade. All right, number 3. ST is the point of tangency. Assume that segments appear to be tangent or tangent, so therefore, since SR is a radius, we must have a right angle again here at the point of tangency. Now, this one's a little bit different. Look what we're trying to find. We want this piece right here, just that. Right, but what can we figure out right now? What can we figure out using the triangle? We got a leg. All right, let's do it. We got a leg and a leg. We can find the entire hypotenuse. That's a HYP, excuse me. 15 squared plus 36 squared equals the hypotenuse squared. Just going to use an H because I don't want to use an X. I don't even know what that is. What's 36 squared? That's not one I've ever memorized. 9,000, I don't know. Come on, guys, help me. So I don't have to, all right, I'll pull my calculator up. I know you did. But I had to do it. 1,296. What did you get when you added those? 1,521, did you say, Sabrina? Thank you. All right, then take the square root. Is that a nice number? Yeah. 39. Why? Why would you divide by 2? Did somebody tell you that the hypotenuse is bisected? Okay, so let's use something more factual. Well, yes, you can. No, you're not. Hold on. Guys, I got to give you a hint. Now, there's something I mentioned earlier that we're forgetting to do in a lot of different situations with circles. Sometimes there's more than one diameter. Sometimes there's more than one radius. Okay, we shouldn't be chatting right now. Thank you very much. Isn't that a radius, guys? So that's 15. Yep. We have to subtract 15. So we just need be a little more observant about what we have. All right, so X is 24 units. Okay, now that might be something you should look for. Let's see if we need to use that idea in the next problem. Identify any radii in the picture. This is 24. This is also 24. Do we really need it though? You see what I'm saying? We want to find that whole X. We don't really need that, but it should tell us that this should be bigger than, our X value should come out to be bigger than 24. Agreed? Okay. We didn't have to use this 24, but we'll go ahead and use the right triangle. So we actually want to find the entire hypotenuse. That's going to be the hypotenuse of the right triangle. The other two are legs. Okay. So we got a right angle here. Doesn't want to draw that for me. All right, so 17 squared. Okay, I got to use a regular pen because that's not writing. Okay. 17 squared plus 24 squared, add the legs and square them, equals x squared. Or the hypotenuse squared, and which is x in this case. All right, it's 289 plus 576, 865. Is that what you told me? Take the square root. This one will be a decimal. Okay, 29.4 units. Pythagorean theorem. You've been using it all year. Circumscribed polygons are next. We'll go about that concept now, where if you have a tangent on the exterior, or a common point from an exterior and two tangents are drawn from it, these would be equal. So in this would be a regular polygon. This is a hexagon drawn about a circle. If it's a regular hexagon, all of these little segments would be equal. Those are all tangents. All those little segments are equal to each other. Now we're going to use it. This is not a regular polygon. This is an irregular triangle, or a triangle that is scalene. We're going to use the concept of, if it's coming from the same point of tangency outside the circle, two other points of tangency. Excuse me, I said that incorrectly. These are both 2. Going this way. These are both 4. It said to find x and the perimeter. Those little markers don't like to write. There we go. Going the other way, 6 here, so we got a 6 going this way. So I just found out x by adding 6 and 4. So x is going to equal 10. And now the perimeter, let's add up those sides. So we got pairs, add 6 and 4 is 10, 6 plus another 4 is another 10, that's 20, and then 2 plus 2, 24. And these are all in units. Can someone suggest what to do for me on the next problem? All right, 2x equals 8. So x is 4. And then the perimeter, well, what is this thing on the outside of this circle? That was 8. You told me this was 8. That's 8. This is 16, so that's 8. That's 8. That's 8, and that's 8. It's a square. We just proved it was a square. So 16 plus 16 plus 16 plus 16, or 4 times 16. You were right, Kate. 64 units around. Okay, then. Homework is next. I'm going to show you how to do the first two because we didn't have an example of that yet. You may think of a way to prove this. You're right, it is Pythagorean theorem, Nathan. Determine whether each segment is tangent to the given circle. What are we trying to prove then? Guys, if HI is tangent to the circle, what must be true? What needs to be true that's not even drawn in the diagram? If you said, thank you, Hannah, the right angle. You want to, this question is that a right angle? Okay, that's what you need to prove. How would you prove that it is? We have proved whether a triangle is a right triangle before. How do you prove that? Come on, I know you guys can figure this out. How do you prove you have a right triangle or not? Okay, Cade. And that has to what? Okay, then let's discuss that. If 9 squared plus 40 squared is less than 41 squared, then it was, now wait, we actually went with the 41 first. Remember that? Okay, if this is less than, then it was acute. If this would come out to greater than, then it was obtuse. If this comes out to equal, then it's a right triangle. So you're trying to decide if this is true or not. That's how you prove there's a right angle there. This must be a right triangle if that is tangent to the circle at point H. So is this, what is 41 squared? Is 9 squared plus 40 squared 1681? Okay, so that means, yes, HI is tangent. It is a tangent. That's what you just proved. It has to be perpendicular to HG if it's a tangent. All right, so look at number 2. It's asking the same question. Is AB tangent to the circle at point A? What would have to be true is this would have to be a right angle, which means this would need to be a right triangle. So is 13 squared equal to 4 squared plus 12 squared? Does that equal 16 plus 144? No, 169 does not equal 160. So AB is not tangent. We are using something we learned in another chapter about proving a right triangle to prove whether this was a tangent or not. Okay, get some of this work done. You need to finish your homework, do the rest of the practice. Be prepared with questions tomorrow so that I can help you out if you have some you did not understand how to do.